Welcome to The Explainer. Today, we're going to break down a classic chemistry technique that's built on a really simple but powerful idea: precision weighing. It's called gravimetric analysis, and trust me, it's way more relevant than you might think.
So let's just start with a real-world scenario. Imagine you've got a painkiller tablet. The box says it has a very specific amount of medicine inside, maybe even a couple of different active ingredients, like a pain reliever and an anti-inflammatory.
And this isn't just a question for medicine, right? It's absolutely critical in everything from checking our environment for pollutants to making sure our food is safe. How can you possibly measure just one specific thing when it's mixed in with a whole bunch of other stuff? Well, the answer lies in a super clever and incredibly precise chemical technique.
Okay, so the solution to this whole purity problem is a method called gravimetric analysis. And honestly, the name itself kind of gives the game away. Gravi has to do with gravity, weight or mass. And metric is just a fancy word for measurement.
At its very core, it's such a beautifully simple idea. If you want to know how much of one specific substance, and chemists call this the analyte, is dissolved in a liquid, all you have to do is find a way to turn only that substance into a pure solid that you can actually pick up, or, well, collect and weigh.
Think about it like this. It's like you're panning for chemical gold. You've got this big mixture of sand and water and all sorts of other stuff, but you only care about the tiny flecks of gold. This technique lets you chemically wash everything else away, leaving you with just the pure stuff you wanted to measure in the first place.
So how do we actually pull this off? How do we do this separation? Well, the most common way is through a process called precipitation gravimetry. And it's not some random thing. It follows a really specific playbook to make sure the result is spot-on accurate.
The whole process is super methodical. First, you get your sample ready by dissolving it. Then comes the magic part. You add a special chemical, a precipitating agent, that reacts only with the thing you're looking for, causing it to crash out of the solution as a solid. After you let those little solid particles grow and get pure in a step called digestion, you just filter them out, wash them clean, dry them completely, and then you head to the scale for that final crucial weigh-in. Let's make this totally real for a second. Let's say you need to figure out how much barium is in a water sample. You'd start with your water, which has some barium chloride dissolved in it. Then, you'd carefully add some sulfuric acid. A chemical reaction kicks off and boom, a solid barium sulfate forms right there in front of you. That's your precipitate. Now, you can collect it and weigh it to figure out exactly how much barium you started with. Okay, so a solid forms, you filter it out, you weigh it. Sounds pretty straightforward, but how that solid actually forms is incredibly important. It turns out the quality of that solid you make is absolutely crucial if you want to get the right answer. And this is where things get really interesting. See, the goal here is to form these nice, big, dense crystalline particles. They're perfect because they settle out fast and are super easy to catch with filter paper. What you want to avoid at all costs is this messy, murky sludge of tiny colloidal particles. They're so small, they just float around and will either clog up your filter or go right through it. Total disaster.
So, how do you make sure you get those good, big crystals? Well, the whole process is kind of like a two-step dance. First, a few ions get together and form tiny little seed particles. That's called nucleation. Then, more and more ions from the solution start sticking onto those seeds, making the crystals get bigger and bigger. That's particle growth. The real secret is controlling the conditions so that you favor growth instead of just making tons of new tiny seeds.
All right, so with all this painstaking work to get a perfect, pure solid, you might be wondering, is gravimetric analysis the perfect method for everything? Well, like any really powerful tool, it definitely comes with its own set of pros and cons.
And the trade-offs are pretty clear. On the plus side, it is exceptionally accurate and precise. And because it all just comes down to a simple mass measurement on a scale, there's very little room for instrument error, and it's pretty inexpensive to do. But the downside? It is not fast. It's a slow, careful, meticulous process, and you can usually only analyze one thing at a time.
You know, in our world of high-tech sensors that give you instant results, a method like this might seem a little, well, old-fashioned, but its fundamental importance as a gold standard for accuracy is just undeniable.
And you can see how relevant it still is. It's a cornerstone of quality control, making sure your medicine has the exact right dose. Just like in that example we started with, it's used to check our water for dangerous pollutants. In fact, it's so reliable it was even used to help determine the fundamental atomic masses of the elements on the periodic table.
So it really all comes back to this one simple, elegant concept.
If you can turn a substance into a pure solid, you can measure its mass directly. It's a tangible measurement of actual matter, and you really can't get much more fundamental than that.
And that kind of leaves us with a thought, doesn't it? In our high-speed digital world, it's fascinating that a technique based on something as simple as weighing an object remains so essential. It really makes you wonder, what other foundational, brilliantly simple scientific ideas are we still relying on every single day?